Welcome to This Explainer. Today, we're jumping right into the fundamental mechanics of math, factorization and algebraic fractions. If you're tackling Form 2 math, specifically Chapter 2, well, you're in the exact right place. Think of today's journey as learning how to use both the building blocks and the dismantling tools of algebra. We're going to see exactly how complex equations are put together and, more importantly, how we can pull them apart. Okay, let's dive into this. Imagine you're looking at a floor plan, right? You need to order a carpet, but the dimensions aren't your simple, everyday numbers like 5 meters by 4 meters. No, instead, the length is 3r minus 2 and the width is r plus 1. So how on earth do you calculate the area when you're dealing with unknown algebraic variables? I want you to keep this real-world problem in the back of your mind because by the time we finish up here, solving it is going to be an absolute breeze.
Here is our roadmap for today. Number 1, the language of algebra. 2, expansion, multiplying it out. 3, factorization, the reverse process. 4, four methods of factorization. And finally, number 5, operating on algebraic fractions. We'll build up your skills step by step.
All right, kicking things off with Section 1, the language of algebra. Before we build anything, we need to know our basic materials. Take a look at this expression here, 2x plus 4y minus 9. Now, we have our variables, x and y, which represent our unknown values. Then that negative 9 sitting at the very end, that's a constant, meaning it has a fixed value, no variables attached. And finally, the coefficients. Those are the numbers directly multiplying the variables, like the 2 in 2x. Honestly, just having a quick grasp of these distinct roles makes decoding the rest of algebra so much easier. Moving right along to Section 2, expansion or multiplying it out. This is where we start building things up. Remember that carpet problem from the beginning? Let's actually solve it. Step 1, we know the area of a rectangle is simply length times width, right? So step 2, we plug in those algebraic dimensions we had. We get 3r minus 2 in one set of brackets, multiplying r plus 1 in a second set of brackets. Now step 3 is where the expansion magic really happens, using the distributive law. Basically, every single term in that first bracket absolutely must be multiplied by every term in the second bracket. So 3r times r is 3r squared. 3r times 1 is 3r. Negative 2 times r is negative 2r, and negative 2 times 1 is negative 2. When we combine the like terms sitting in the middle, the 3r minus 2r, we are left with our final expanded area, 3r squared plus r minus 2. Just like that. Now, a super quick but absolutely vital reminder for you. When you're doing combined operations with all these algebraic terms, the trusty BODMAS rule still dictates everything. You always prioritize brackets first, then orders or powers, followed by division and multiplication, and finally addition and subtraction. Remember, just because we threw some letters in there, algebra doesn't change the foundational, rigid rules of arithmetic. Let's flip the script and head into Section 3, factorization, the reverse process.
So, the crucial point I really want you to take away here is that factorization is quite literally just walking backwards. Think about it. Expansion takes factors and multiplies them to build a larger expression. Factorization takes that larger expression, uncovers the original factors, and securely packs them right back into brackets. It's the ultimate teardown. So if you can understand the logic of expanding, guess what? You already possess the logic needed to factorize.
Which brings us to Section 4, the 4 methods of factorization. Let's see how this builds our toolkit. Depending on the specific structure of the math expression sitting in front of you, you're going to need a different tool to deconstruct it. We've got 4 main methods here: the highest common factor, the difference of squares, cross-multiplication, and grouping. Let's break these down one by one. Okay, method 1 is the highest common factor, or HCF. You look at your terms and simply pull out the absolute largest factor they share. For instance, between 8x and 12x squared, both can be divided by a maximum of 4x. So you just pull that 4x out to the front of a single bracket. Easy enough, right? Method 2 is the difference of squares. Honestly, this one is a brilliant shortcut. If you happen to have 2 algebraic terms that are perfect squares subtracted from one another, like 4x squared minus 9, it perfectly, and I mean perfectly, splits into 2 symmetrical brackets, 2x plus 3 times 2x minus 3. It is incredibly satisfying when you learn to spot these perfect squares in the wild. Now for method 3, cross-multiplication. This is your go-to for standard quadratic expressions, like x squared plus 6x plus 8. We're going to systematically walk through this 5-step process. First, we compare it to the standard form, which is ax squared plus bx plus c. Here, our C is 8 and our B is 6. Now, why does this matter? Because the whole logic requires us to find factors of our C term, which is 8, that will perfectly add up to our B term, which is 6. Well, the factors of 8 are 1 and 8, or 2 and 4. Which pair adds up to 6? 2 and 4, of course. After doing a quick cross-multiplication check just to verify everything lines up, we pack them right back into brackets. Our final result is x plus 2 multiplied by x plus 4.
And method 4 is grouping. You pull this one out when you're faced with a slightly longer expression, specifically 4 terms, like PQ plus QR plus PS plus RS. It looks messy, but all you do is group them into pairs that share common factors. Then pull out that common factor from each pair, and finally factorize those groups together. It basically allows us to isolate the chaos and methodically pull everything back into 2 tidy brackets, in this case, Q plus S times P plus R.
Finally, we reach section 5, operating on algebraic fractions, the final boss. This is where we take all those shiny new expansion and factorization skills and apply them. Now, adding and subtracting algebraic fractions follows the exact same rules as regular fractions. If the denominators match, you just simply add or subtract the numerators straight across. No problem. But what happens when our denominators don't match? Well, just like with middle school math, we are completely stuck until we find the lowest common multiple, or LCM, to make those denominators identical before we combine anything.
And this example right here brilliantly illustrates how we methodically scale up different denominators. Let's say you have one fraction sitting over 4p and another fraction over 6p. First things first, we find the LCM. We divide 4p and 6p by their common factor, which happens to be 2p. That leaves us with remainders of 2 and 3. Then we simply multiply that common factor by those remainders, 2p times 2 times 3. That gives us 12p. 12p is our common ground. We can now scale both fractions up so they sit nicely over 12p, and then we can easily add those numerators together.
When it comes to dividing algebraic fractions, the rule is surprisingly simple. Division is really just multiplication in disguise, right? You simply take the second fraction, the one sitting after the division sign, find its reciprocal by flipping it completely upside down, and then just multiply straight across. Numerator to numerator, denominator to denominator. It's a lifesaver. Okay, before we wrap up today, I need to let this rule burn into your memory because it avoids one of the single most common pitfalls in algebra. Listen closely. You can only cancel off whole factors. You absolutely cannot cancel terms which are part of what is inside a bracket. If you have an x plus 2 trapped inside a parenthesis, you cannot just cancel out the x with another x sitting on the bottom of the fraction. No way. You can only cancel whole factors. Never break into a bracket to cancel a single term. And there you have it, folks. From discovering the precise area of a tricky carpet using the distributive law to smoothly scaling up complex algebraic fractions, you now hold the structured tools to not just build up complex expressions, but to confidently deconstruct them. So the very next time you look at a complex system, whether it's in a math textbook, coding, or even architecture, ask yourself, how was this built? And more importantly, how would I take it apart? Keep exploring, keep questioning, and I'll see you in the next explainer.